Welcome. Today we are going to discuss the chapter of magnetism, right? So I'm going to begin with a quick analysis of this chapter based on the number of questions that came in the JEE papers. And then we'll go through a quick summary of this chapter, and then we'll of course solve some problems, okay? So let's start with advanced. In JEE Advanced, in 2018, there were two questions asked from this chapter. One of them was from the concept of magnetic field due to a loop of current, and the other one was from the motion of charged particle in a magnetic field. In 2017, there were 5 questions asked from magnetism, and that's a lot of questions, okay? So there was one question which was based on motion of charged particle in a combination of electric and magnetic field. There was a separate question which dealt with motion of charged particle in magnetic field alone. And there was question based on the magnetic field due to straight wire and also the magnetic field due to an arc, okay? Surprisingly, in 2016, there were not a single question asked from magnetism, which was a rare case, because usually you see 2 or 3 and up to 5 questions have been asked from this chapter. In 2015, there were 3 questions. One of them was from the field due to arc and straight wire, and the other one was based on the force acting on a moving charged particle, all right? And if you talk about 2014, again there were 3 questions. Again, a field due to an infinitely long wire, then field due to loops, and again in another question which combined loops and infinite wire, and there was also a question on magnetic moment. So you see, in general, a lot of questions are asked where you have to find magnetic field due to infinite wires and loops, and how does the charge behave in a magnetic field, right? If I talk about JEE Mains, then in 2018 there were 2 questions. One of the question again was from motion of charged particle in magnetic field, and other was from magnetic field due to a loop, okay? In 2017, surprisingly, there was absolutely no question asked from magnetism. In 2016, there was just one question, and that was again from in the magnetic field due to a wire, this time a finite wire, and of course loops. In 2015, again there were 2 questions. One of them was based on torque on a current carrying wire, which is a rare question which gets asked if you see the trend in the last 5 years. And there was a question on force on a current carrying wire. And in 2014 there was just one question which is based on magnetic force. So you see, you can expect 1 to 2 questions from magnetism in your JEE Mains paper. So now let's get on with the summary of this chapter, right? So interesting thing is this entire chapter of magnetism, in fact these are 2 chapters, right? Magnetic force and magnetic effects of current. This entire magnetism revolves around this concept of vectors that you really need to understand. And if you don't understand that, you are going to have a lot of trouble, and you must have already faced, if you have done this chapter before, in understanding magnetism. So I have a little prop here with me, right, to help me with that. So now let's say, so what we're going to do is we're going to find cross product, right? How to find cross product between 2 vectors. So if I have, say, 2 vectors A and B, let's say this is my vector A and this is my vector B, right? So this is A and this is B, right? And I have to find A cross B. How would I find A cross B? So the first thing you have to realize about when you find A cross B, when you hear the term A cross B, okay? Imagine a plane that contains both A and B. So this is A and this is B, right? This is the plane that contains both of them. You can imagine this plane, right? This plane over here, the plane which contains both of them. So this is A and this is B, right? Now, once you can imagine that plane, when you are asked to find A cross B, all you have to do is use your right hand, don't use your left hand. Project your fingers in the direction of A and then curl it towards B. See, I'm projecting the fingers in the direction of A and curling it towards B. The thumb gives you the direction of the cross product. It is A cross B, right? A cross B is a vector, which means that it is in the direction of this red axis, all right? Now, this is A cross B. Another interesting thing is, the reason I asked you to imagine that plane is because this vector, the A cross B vector, is a vector which has to be perpendicular to this plane, right? So if both of these guys are making a plane, right, A and B, then A cross B will always be a vector perpendicular to that. That means that it is perpendicular to A as well as to B, okay? So you can see that this red axis is perpendicular to this A as well as to B, and that's very important to understand, okay? Now let's say I had to find B cross A. So in that case, what will I do? I'll take my fingers in the direction of B and curl it towards A, and the thumb gives me that direction, right? It means that B cross A has this direction, which is perpendicular to their plane, perpendicular to both A and B. See, you can see that A cross B is opposite of B cross A. You see the magnitude of A cross B is AB sine theta. Magnitude of B cross A is also AB sine theta or BA sine theta, the same thing. But the direction would change, right? The direction of A cross B will be here, the direction of B cross A will be exactly the opposite. So this is one very important thing which you need to learn here, right? How to find cross products. And if you know how to find cross products, then you can do a lot of tough stuff in this chapter. So again, I want to emphasize on the fact that the cross product of two vectors is another vector, and the direction of that vector is such that it is perpendicular to both A and B, and we use the right hand curl rule, let's call it, to find the cross product. There are other rules also. This is the rule which I find the easiest to follow. So that's how you find the cross product. And if you know that, then this chapter becomes very easy for you. Now let's get on with the actual chapter. Now magnetism is basically divided into two parts, right? The first part we study the magnetic force. With the magnetic field given to us already, we don't care about from where this magnetic field is coming. It's something which is just there. Okay, they just tell you that this is the magnetic field, this many Tesla. Now find the force, find the force, find the force. Find the force is the first part of magnetism. Second part is where the magnetic field is not given and you are asked to find the magnetic field. So the first part is find the force, the second part is find the field, right? So let's talk about finding the force. Now if you have a charged particle in a magnetic field, and if the charged particle is stationary, then the force that charged particle experiences is zero, right? So if you have a magnetic field in a region, let's say the magnetic field is in this direction, there's a charge quietly sitting, not doing anything, it will not experience any force, no matter how strong that magnetic field is. This guy will be like, okay bro, nothing, okay? But if the charged particle starts to move, if it has a velocity, then there's a possibility that it will experience a force. And I'm saying it's a possibility because you see, magnetic force is equal to Q times of V cross B, right? So you see the cross product coming on there. Now, if V and B happens to be parallel, that is if the velocity and magnetic field happens to be parallel, in that case, VB sine theta, right? Theta will be 0, so VB sine theta will become 0. In that case, there will be no force. So if there is a magnetic field in this direction and there is a charge also moving in the same direction, that is V and B are both parallel or anti-parallel, but basically in the same line, then what will happen? There will be no force. So only if there is a charged particle in a magnetic field which is not moving parallel or anti-parallel to the magnetic field will it experience a magnetic force, okay? And what a force? This force is going to be always perpendicular to the velocity, because you know the product of V cross B is a vector which is perpendicular to both V and B, okay? What is strange thing about this? A strange thing about a force which acts perpendicular to the velocity, right? Because if a force is acting perpendicular to the velocity, it means that it is always perpendicular to displacement, the change of position. And if a force is always perpendicular to displacement, it means that it's not doing any work, right? You remember the concept of work, right? Work is force F dot dx, we call it, right? So if F dot dx, if F and dx, they are both, or dx vector and F, they are both perpendicular, then this is going to be 0. It means that the magnetic force does not do any work on any charge. That's a very important thing to remember. So so it doesn't change any kinetic energy from the work energy theorem, you can get that. So these are certain things. Now there are some interesting cases. So one of the interesting cases when V is perpendicular to B, okay? When velocity is perpendicular to B, then what happens? So here you can see that I have made this case where V is perpendicular to B. So here is my V, and if B is perpendicular, I have drawn a circle here already. You can see that this bigger circle. What will happen? So let's say this is the direction of V, right? And B is perpendicular like inside, right? Then V cross B, curl your, stretch your fingers in the direction of V, curl it in the direction of B, and V cross B will give me the direction of the force, right? And if it happens to be positive charge, it will be upwards. If it happens to be negative charge, it will be downwards. So let's assume positive charge for now. Positive charge, the direction of force is upwards. It means that there will be a centripetal force acting on this thing, right? Because force is always acting perpendicular to the velocity. It has to be centripetal, and it'll act in the upward direction. It means that it'll undergo a circular motion with the center in the upward direction, right? So it will move like this in a circle, like this way. So this is a summary, so I'm assuming that you've already gone through a chapter a little bit, right? So I'm just trying to revise everything. So it moves in a circle in this format. Now interesting thing is, anytime you get a question where you find that the velocity is perpendicular to the magnetic field, all you have to do is find the direction of the force, right? By using Q times V cross B. That direction gives you the direction of the center of that circle, okay? It means that the center of the circle is here. This is the direction of Q times of V cross B. This is the center, okay? And the circle is such that the initial velocity V acts like a tangent to that circle. So this is like acting like a tangent. So these are the two things that I remember every time. Every time I see a charge in a magnetic field which is perpendicular, how will the circle be? Will it be like downwards, upwards? What is the like direction of the radius, like the center and all that? So all that confusion, I just have to remember these two points. One is V cross B, in case of positive charge, will give me the direction of the center. Negative charge, opposite will be the direction. Cool. The second thing is V would act as the tangent, right? Initial velocity will act as a tangent. So I can very easily draw a circle like that. Now, a lot of discussion are done about this circle. You can find the radius of this circle. There are different methods. I'm not going into that. Basically you can equate the centripetal force to the magnetic force. So the R comes out to be mv by qb. That's important. So it means that the higher the speed, the more will be the radius. So in the same magnetic field, the same charge, if it moves with a higher speed, it means that it will move in a circle of greater radius, or its curvature will be less. It will be less prone to curve in the sense, right? Because it's moving with a high speed. You can see it that way. And then another expression is for the time period. Time period is 2 pi m by qb, right? And that's another interesting thing, because time period does not depend on speed. So if you have the same charge and the same magnetic field, and if you project two charges, one with a higher speed and one with a lower speed, the higher speed charge will cover a bigger circle, and the smaller speed charge will cover a smaller circle. You have to imagine that. So the higher speed charge is covering a bigger circle, and the smaller speed charge is covering a smaller circle. But both these guys have the same time period. It means they start at the same time and they come back at the same time, right? So time period is independent of speed. That's a very interesting thing that you have to remember. Now we come to the third idea. When the speed of the particle, the velocity of the particle, is neither perpendicular nor parallel to the magnetic field. It's neither perpendicular nor parallel. So it has a magnetic force on it, and that magnetic force would manifest in a way that will be different from like moving it in a perfect circle. So what happens here is the case here, right? So I have a velocity v, and I have a magnetic field here b, okay, and you can see that they have an angle between them, theta. So now how would I deal with a question like this? So now to deal with a question like this, what I'll do, I'll take that my velocity, and I'll resolve it into two components, perpendicular and parallel to the magnetic field. So when I do that, so the part of the velocity which is parallel to the magnetic field will not have any effect, right? Because there's no force in that direction. So there will be no force in that direction to the charge in that direction. It means that its speed in the parallel direction of the magnetic field is always going to be v cos theta. It's not going to change. But in the perpendicular direction, because there's a speed and there's a magnetic field, there will be a force. But force will not be in the perpendicular direction there, right? It will be v cross b. So v cross b, the direction will be inside, okay? So this v will act as a tangent, and that is the direction of the center. So it means that the circle must be of this nature, right? The circle would be like this, right? This is my v, and this is the b, and that is the force. So circle is like this, but because there is a v cos theta also, it means that it will also have a velocity in the forward direction. That means this guy will keep moving in a circle. At the same time, it will also move forward. So it keeps moving like this, but forward also. So, it will come towards me like this. Okay, and that's called a helical path, and that's how in a helix this object would move. Now we are done with calculating the magnetic force on a moving charge. The next thing is, what would be the magnetic force on a current carrying element? Because in a current carrying element there are moving charges. So there's a straight formula. It is I times of L cross B. So if you have a straight wire like that, you imagine that there's a length vector L along its length, which is L. You do L cross the B. So in this case, L cross B, when you do, you'll get the direction of the magnetic force like this, right? L and the cross B will fetch you a magnetic force in that direction. Okay. Now, if that loop happens to be curved, then the magnetic force can be found out by connecting the endpoints of that loop. If it has a current I, then I can connect the endpoints. I can take this element, call it some L, and find the force on this element. And whatever is the force on that element, that is the same force which is acting on this entire loop. Okay. Now, there's another concept, which is the concept of magnetic moment. So if you have a current carrying wire which is carrying a current of I and has an area A and the number of turns is N, then we define a new quantity called as magnetic moment, which is I times N times A, or NIA, right? And it has a direction, it's a vector, right? So what you do is you curl your fingers in the direction of the current, right? You curl it like this. The thumb gives you the direction of the magnetic moment, so it will be inside the plane in this case, right? And you can find torque on a current carrying wire using the concept of magnetic moment as well. So torque is equal to M cross B, and the potential energy at any point is given by U equals to minus M dot B. Okay, so in a specific orientation of this loop with respect to the magnetic field, you can find the torque acting on this loop as well as the potential energy of this loop if you know its magnetic moment. Now we come to the second part of this chapter, which is about calculating magnetic field or finding magnetic field, right? So the first thing which you encounter here in this chapter is Biot-Savart's law. It's actually pronounced Biot-Savart's law. Some people have an issue with that. So Biot-Savart's law basically tells you that if you have a wire, right, a random wire, you can find the magnetic field because of that small element of that wire at a point. So if you choose this to be a point, let's say this point is P, I can find the magnetic field because of a small element dl of this wire, okay, at P. So for that I have to define a vector R which joins this point and this point, right, which joins, let's say, point B to point P, alright, and I define it to be a vector, and the formula then for which comes from the Biot-Savart's law is equal to mu naught by 4 pi I times of dl cross R by R cube. So this gives you the magnetic field due to that small element at that point P, and then you have to integrate, making sure all the vectors are in the same direction and find out the net magnetic field. So for some peculiar shapes, we have found that, and you're encouraged to remember some of the formula because it makes calculations a little quick. So for example, you have a straight wire, right? If you have a straight wire and you are supposed to find magnetic field at a point over here, which is at a distance r from it, and let's say this angle here is alpha and this angle here is beta, then that is given by mu naught I 4 pi r sine alpha plus sine beta. Okay, that. And if you have a circular current carrying loop and you have to find the magnetic field at a distance x from that loop, then the formula is mu naught n I r square by 2 r square plus x square whole to the power 3 by 2. I'm just reminding you of that, where n here is number of loops, r is the radius, x is the distance from that ring. Okay, when you make x 0, you come to the center of that ring, okay, and that would give you the magnetic field at the center of the ring. So when you make x 0, what do you get? You get mu naught ni by 2r. That's the magnetic field at the center of the ring. Now there is also magnetic field due to an arc, right? So the magnetic field due to an arc that carries a current I at the center is given by mu naught I 2r theta by 2 pi, where theta is this central angle. So if you know the theta, then you can find the magnetic field at the center, right? And the way you find magnetic field in that case is that you curl your fingers in the direction of the current and the thumb gives you the direction of the magnetic field. So in this case, it will be inside the screen, okay? And there's another formula for the magnetic field inside a long solenoid, and that's mu naught times Ni, and that's the formula which is, let's say that's a magnetic field which is for a point which is very close to very close to the axis of that solenoid, right? And again, to find its direction, you have to curl your fingers in the direction of the current, and the thumb will give you the direction of the magnetic field. All right. So all these little formulas, they're not a lot. If you remember them, you would be able to save some time in your paper, and that's kind of becomes important for JEE. Otherwise, I don't recommend remembering a lot of different formula. Now, So the last thing which I want to discuss here is the Ampere's law. So what we do in an Ampere's law is we choose an imaginary loop. Okay, if you choose an imaginary loop in space, any loop, we say that the circulation of magnetic field in that loop is equal to mu naught times I enclosed. Now what does that mean? So there is this term defined called circulation of magnetic field, which is basically equal to B dot dl. B dot dl. Okay, B is the magnetic field and dl is a small element in that loop. So I can choose any direction, any dl. So if I choose a small dl here, for example, dl is this element. Dl is a small element in that loop that runs all about that loop. Okay, so that dl will be like that can move along that loop when I integrate that. Now B dot dl, okay, the entire circulation is the integration of B dot dl in a closed loop. So I put this small circle there. This is equal to mu naught times I enclosed. So here what all charges are enclosed? See, I1 and I4 are not enclosed by this loop. Okay, so they're not part of my discussion, they're not part of my equation. I2, I5 and I3 are. But you see, I2 here is going into the plane, whereas I5 and I3 are coming out of the plane. Right? So what should I write? Mu naught times I2 plus I5 plus I3, is that correct? Right? No, right? Because I chose the direction of dl, that kind of also fixes the direction, the positive direction of current. You can see it like that. Okay, so if I move my fingers in the direction of dl, I see that the direction in which the direction of my thumb is into the plane, right? So I can consider the direction into the plane to be positive. When I do that, what happens? I2 becomes positive and I5 and I3 becomes negative. So this is not right. I can write this is equal to mu naught times of I2 minus I5 minus I3. Okay, and that's how you apply the Ampere's circuital law. So in this question, you are given an insulating rod of length L and there's a uniform charge distribution over that rod, and it is pivoted at its midpoint and it is being rotated with a frequency. Now we are supposed to find the magnetic moment of this rod, and now this question kind of feels like weird in the beginning because I know how to find magnetic moment because of a current carrying loop, right? If I have a current carrying loop, it's very easy to find the magnetic moment. If I know, like, say the current is I and the area is A, then it is I times A. If the number of turns is some N, then N times I times A gives me the magnetic moment. But here I don't see any current. There's this charge and then this loop which is moving. See, you can find the magnetic moment of this particular configuration if you understand that whenever there's a motion of charge, there's current, right? So there are charges moving here because this thing is rotating. So now what you have to do is forget about the entire charge in that rod. If you just concentrate at one fixed point over there, see, it has some charge there, right? And its counterpoint, which is on the other end, that also has a charge. Now these 2 points have charge, and when this thing rotates, it is sort of like they're forming a loop. It's sort of like a charge which is moving in a circle, isn't it? Both these charges are moving in a circle. So that constitutes a current, isn't it? Now if you concentrate at one of those charges, right, you see that the number of times it moves through that fixed point in 1 second is f, right? It moves through that fixed point f times in a second, right? So what would be the current because of that small charge? Let's call it dq. The current will be dq times f, because per second, that is the number of times it is moving, right? That will be simply the current, right? Because frequency, you can also say it's one by time period. So you need dq by t, that is dq times f, right? Because 1 by t is equal to f. So you can very easily find the charge, the current, because of that small charge. Now let's say that charge there is at some distance x from the center. Okay. Now what I can do is, I can write the magnetic moment because of that small charge, right? I can say that the magnetic moment dm will be equal to the I there times the area of this circle which it is covering. Now what will that be? That will be equal to dq is the charge times f, this is the current, I just told you how, right? This is the current, times area will be pi times of x square, because that is the circle there, right? Now this will give me the dm because of that small element, right? Now what I do? I can write that dq as equal to q by the total length, which is L. So this will kind of give me the linear charge density times dx if the length of that part is dx, right? So dq can be written as qL by dx times of f we have, then pi we have, then x square we have, right? So this is a neat little equation that you have gotten, which is the magnetic moment of that small part. Now all you have to do is integrate it, because magnetic moment from all those circles, all those loops will be in the same direction, right? If it is moving like this, it will be in the inside direction. If it is moving like that, it will be in the outside direction. So, it will be in the same direction. That's the point. Now I'm going to integrate this. So when I integrate this, integration of dm, I get integration of q by L dx f pi x square. Now from where to where would this integration run? See, x value is running, that is my center. So x runs from minus L by 2 to plus L by 2. So minus L by 2 to plus L by 2 it runs. So this becomes, okay, q by L, f and pi, these are all constant I can take out. I get integration of x square dx, which is equal to this constant times integration of x square will be x cube by 3, x cube by 3. So, and what are the limits, by the way? So limits here is minus L by 2 to L by 2, right? What does that become equal to? Let me take it over here. This becomes equal to q by L f times of pi L by 2 whole cube by 3 minus of minus L by 2 whole cube by 3, and when you find that, you get q pi f L square by 12. Simple calculation will get you that result. In this problem, there are uniform electric and magnetic fields, and the strengths are given E and B, and they're along the y-axis, okay, and the diagram is shown to you. Now, there's a particle with a specific charge of q by m, that is charge to mass ratio is given to you, and it leaves the origin with an initial non-relativistic velocity v0. It means that the initial velocity v0. Don't worry about non-relativistic and all that stuff. Now to solve this problem, I have this coordinate system. This is my x-axis, this is my y-axis, and that's the z-axis, okay? So what you're given is that there's an initial velocity in the x direction, and then there's magnetic field in the y direction, and there's also an electric field in the y direction. So let's forget the electric field for now. Let's just concentrate on the magnetic field. Now this is V and this is B. So when you find V cross B, how will you find that? V, right? You project your fingers in the direction of V, curl it in the direction of B. The thumb gives you the direction of the force. So that is the direction of the force. It means that the center of this circle would lie somewhere along this line. It means that this particle would move in a circle which would look like this, right? Something like this, like, this would act as a tangent and it'll go something like that. Now, because there's also an electric field which is trying to push it upwards, right? There'll be, so the pitch of this helix would keep increasing because there's a force in the upward direction, right? So it'll be a spiral, right? With the pitch increasing with each and every turn. So it'll be like it started from here, it took a turn, it came over here, and then it took a turn, it came to a bigger direction. So it's sort of like for that helix, the spring is sort of getting stretched as you're moving more and more towards the z-axis, okay? So that's how it goes. So after one turn, it'll come to some point and cross y-axis, and after another turn, it'll cross y-axis again, and another turn, it'll cross y-axis again. So the time period, because it's independent of speed, is 2 pi m by qb, right? The time period is independent of, because b is fixed, so it is independent of whether there's an electric field or not. So the amount of time it takes to do one turn is going to be constant, whether that turn is stretched or not, right? So that's just 2 pi m by qb. Now, I have to find at what point does it hit, or at what distance from the origin does it hit the y-axis, or what is the y coordinate when it has made n turns, okay? So there's a force in the y direction, right, because of the electric field, which is q times of E. Now, because of that, there's an acceleration in the y direction, will be q E by m. Cool. Now, if after n terms, what will be the total time for which it has traveled? If t is the time period, which I told you is 2 pi m by qb, then the total time for which it has traveled would be 2 pi m qb times n, that is 2 pi nm by qb, right? That is the total time. Now I have here a motion. If I just talk about y-axis, in the y direction there is a constant force, so there is a constant acceleration, and I have to find where will it reach in the y direction after a specific time. So I can use the equations of motion, right? Because equations of motion can be used when the acceleration is constant. So I can say y is equal to y naught, which is the initial value of y, plus u by t plus half a by t square, right? I can say that. Now y naught, that is the initial value of y, is 0 because it starts from origin, and initial velocity in the y direction is also 0 because the initial velocity was in the x direction, and in the y direction it had no velocity, but because there was an electric field, it started to move. Electric field doesn't require an initial velocity for the force to act, right? You know that. Now plus half a t square, a here is qe by m, t is, we just found, was 2 pi nm by qb, square that, and you get the answer of your y to be 2 pi square mn square e upon qb square. So at that particular value of y, it would have covered n complete turns. So in this question we have a cylinder of radius r, and from that cylinder we have cut out another cylinder of radius r by 2, right? You can see that in the diagram which is given. Now there is a current flowing in the remaining of the cylinder which is equal to I, and we are supposed to find the magnetic field strength, okay, which is, so we have to basically find it for at the point A as well as at the point B, okay. Now how would I solve this problem? Now when you have like a cylinder, the best thing to visualize it is from the top view. So let's take its top view, which will be a circle, right? So if you have a circle like that, right, and if there's a current flowing through that circle, like into the plane or outside the plane, it can be in any direction. If I have to find the magnetic field at a point, let's say there, okay, at that point outside, then what would I do? The magnetic field there is given by mu naught I by 2 pi r, where mu naught I enclosed, to be precise, divided by 2 pi r is the distance from the center to that point. Now this is a result which comes from Ampere's circuital law. I'm not going into the details of how it comes. You can, it's very simple, right? Now if let's say that point happens to be inside that cylinder, like inside that circle like that, right, then what will happen? In that case the formula will be mu naught I enclosed, but in this I enclosed you will have only that current which is in that region, right, divided by 2 pi r, which is that distance, okay. So those are our formula that we have to use. But now the problem is the question, the cylinder which is given to us, when I see the cross section of that, it looks something like that, right? And that shape, that moon-like shape, I don't know how to find the magnetic field because of that. So what should I do? Now what I can do is, I can find the magnetic field because of that entire circle or that entire cylinder, right? And I can also find the magnetic field because of that small portion, the small circular part or small cross section, right, or that small cylinder. And what I can do is I can subtract these two things. So it's like I'm considering that that cylinder to be completely full, right, and I'm finding the magnetic field. Then I said no, this shouldn't be accurate because I've considered it to be full. So let me find the magnetic field because of that small portion and subtract, so that get the accurate magnetic field, right? I can do that. So what I'm going to do here is I'm going to find the magnetic field both at A and B by using this idea where magnetic field is equal to magnetic field because of the whole circle or the whole cylinder minus the magnetic field because of the small cylinder, the small circle cross section, okay. Now how am I going to go about this? So let's talk about A. So if I take A, that point which is at the center, for the whole circle, that point is at the center. So the magnetic field there would be 0, right? So if I talk about BA, the magnetic field because of the whole circle is 0. Now what about the small circle? So for small circle it will be minus mu naught times of I enclosed upon 2 pi times the r, which in this case I know is r by 2, right? But what is the I enclosed? How much current is enclosed? I don't know that. I know that in that moon-like structure, the current which is flowing is I, right? So what I can do is I can find the current flowing per unit area in that structure, right? So I can say that the current flowing per unit area or current surface current density would be equal to I divided by pi r square, that's the area of the whole circle, minus pi r by 2 whole square. And what do I get out of this? I get I 4I by 3 pi r square from this. Rho is equal to 4I by 3 pi r square. Now this is the current density, right? If I know the current density, then I can imagine what would be the current flowing through that portion which is not there, but we are pretending that it is there, right? What will that be? The area of that part is pi r by 2 whole square, right? If I multiply that area with this surface current, I'll get the current flowing in that small part. So the current flowing in that small circle, let's say, is equal to rho times of its area, which is pi r by 2 whole square. When you multiply them, you get I by 3. Okay, so it means that an I by 3 current is flowing through that small area. So now I can come back and I can write BA is equal to 0 minus mu naught I by 3 upon 2 pi times r by 2, and that becomes equal to minus mu naught I upon 3 pi r. Okay, that means that there is no magnetic field contribution because of that whole circle. And if I consider the current to be inside the plane, it can be outside the plane because the direction is not relevant. You would find that the magnetic field is to the downward direction here at A, right? So that's why you can take it as negative. Or if it would have taken it the direction of current to be outside, then the magnetic field would have been upwards, and upward would have been your negative direction. That doesn't matter. You need the magnitude of that magnetic field, and that is mu naught I by 3r, and that's how you find it. Now let's come to the point B, right? When I come to the point B, I see that point B is situated exactly at the center of the small circle. So that the contribution because of that small circle at B for its magnetic field is going to be 0, right? So I can directly write that this term is going to be 0. What about that whole circle? For the whole circle, if I write the formula, it will be mu naught times I enclosed, don't forget that, divided by 2 pi times of r. In this case, r here is r by 2. So 2 pi r by 2. But what is I enclosed? Now I know that the rho we had found out to be 4I by 3 pi r square, right? And that what is the area of that space? That area of that space is pi times of r by 2 whole square. So that is the total current which is enclosed in that region, right? That's how you use the Ampere's law. Now this becomes how much? This becomes again I by 3. So I can write this equation to be equal to mu naught times of I by 3 divided by 2 pi r by 2. So this 2 and 2 gets cancelled. I get mu naught I by 3 pi r as the magnetic field at point B. So in this question, you are given a wire carrying current, and it's in some peculiar shape here, where you have two semi-infinite straight sections and an arc, and the arc subtends an angle theta. It is given that the magnetic field is 0 at the center. Then what must be that angle theta, right? Now the first thing is you have two semi-infinite wires. What is the magnetic field because of a semi-infinite wire, right? So see, even before that, you have to realize that in this problem, I can break this problem into 3 parts. Okay, I can have a semi-infinite wire. I can find the magnetic field because of that, then magnetic field because of this arc, and the magnetic field because of the other semi-infinite wire. So if you and then add or subtract or whatever, depending on the direction of the magnetic field, I can solve this problem, right? So then the question comes, what is the magnetic field because of a semi-infinite wire? Now, because of a finite wire, we know the formula is mu naught I by 4 pi r sine alpha plus sine beta, right? Now, when this point comes to this end, right, over here, right, it goes over there like that, and this kind of extends to infinity, right? Then what happens is that this alpha, as this keeps shifting here, the alpha becomes smaller and smaller, and when it comes over here, alpha becomes 0, right? This alpha becomes 0, and beta because that other point is like infinitely far, so that beta is 90 degrees, pi by 2. So sine pi by 2 becomes 1. So the formula is mu naught I by 4 pi r. This is what it becomes. So this is a formula it won't hurt to remember. Mu naught I by 4 pi r is the formula of magnetic field of a semi-infinite wire at a point on its edge. Okay. Now what? Now let's look at this. For this wire over here, if I see the current is flowing like this, and the point is over here, so the magnetic field will be in the outward direction like that, right? And what will that value will be? There will be mu naught I by 4 pi times of the distance is r, right? Now because of the other wire, it is the current is flowing like this, and the point is over there, so it is again outside the screen. So that is again mu naught I by 4 pi r, and because both the magnetic fields are in the same direction, I can add them, right? So this is the net magnetic field in the outward direction. Now let's see, because what's the case with the arc. So now when I look at the arc, when I curl my fingers in the direction of the current, the thumb gives me the direction of the magnetic field, right? And the magnetic field here we can see clearly is in the inward direction, the inside the screen. And what is that value? So if you remember, the magnetic field because of an arc is given by mu naught I by 2r theta by 2 pi. And this is in opposite direction. That makes sense because the net magnetic field is 0. So the one in the inside direction must be equal to the one on the outside direction, right? The one which is going inside the screen must be equal to the one going outside of the screen. So they must be equal. So when I equate that, I get a hope to find the angle theta. Now mu naught I just gets cancelled here. R also gets cancelled. Okay, I am left with 4 pi also gets cancelled. So this basically becomes 2 is equal to theta by this 4 pi has gotten cancelled, is equal to theta. That's it. Theta is equal to 2. So the value of theta is 2 radians. Hi, so in this problem we have a uniform conducting rectangular loop which is horizontal, although it doesn't look properly horizontal in the diagram, but imagine it to be horizontal, right? Perfectly. And there are two strings that is holding it, vertical strings, and there's a magnetic field in the region with the direction of which is given to you, and we have to find the value of tension which is least. The first thing is, what does that mean? So here we have a magnetic field like this, right? In this direction. If I just let me just name these things, okay? So let's name this as P, Q, R, S, and these 2 points are of importance. So let me name them A and B, okay? So now what will happen is there will be a force because of this magnetic field. Now the force on the limb PQ will be how much? That will be 0, right? Because PQ, the current is parallel to the direction of magnetic field or anti-parallel to it. That is, it is in the same line as the magnetic field. So there will be no force on PQ. There will be no force on SR as well. There will be force only in PS and QR. So if I talk about PS, if you do the right hand thumb rule, you'd find that the force on PS is I cross B. That means it will be in the upward direction, right? So here the force is in the upward direction like this. And how much will that be? It will be I times B times of B. That much force is acting here in the upward direction. What about QR? In QR again, if I do I cross B, I find that the force is acting in the downward direction. So that will be like this over here. I, B, B. Okay. So we have found out the forces which is acting. Is there any other force? There are 2 more forces, right? The tensions. So a tension would be acting here in the upward direction. Let's call it T1. And there's a tension here acting again in the upward direction because tension always pulls. Here this is T2. So I've got T1, T2. I've got the forces because of the magnetic field. Okay, I think I've covered all the forces here. No, but wait, there's mass as well. So there's going to be weight. And weight will act at the center of mass downwards. So there's an mg acting from here downwards. Okay, now I think I've covered all the forces here. Now let me do the analysis. Now here clearly T1 and IBB, they're both working together on one end, and on the other end T2 and IBB are working in opposite direction. such that this loop is kind of maintained in this horizontal position. It means that there shouldn't be any torque on this, right? Of course, the net force in the upward direction must also be equal to the net force in the downward direction. So I can say from there that T1 plus IBB plus T2, right? That is all the forces in the upward direction minus IBB, that's a force in the downward direction, minus mg must be equal to 0, right? So if I can cut these two things out and I can say that T1 plus T2 equals to mg. Okay, let's see if it is of any use here. Now what else is there? So here clearly IBB, the force because of the magnetic field, is having no contribution in the translational motion, right? Because it gets cancelled. What about the rotational motion? What about the torque? So let me find torque about any of the points. Let me do it about B. Okay. So about B, there will be no torque because of T2. There will be no torque because of the magnetic force acting at B. There will be torque because of T1 and this magnetic force, and there will be torque because of this mg. So let's find that. So that becomes torque about B will be equal to IBB, that is the force, times the limb. The limb length here is L, right? And that is trying to rotate it in clockwise direction, plus T1 times the limb length again is L, that is again also trying to rotate it in the clockwise direction. Then I have got mg, that is trying to rotate it in the anti-clockwise direction. So plus mg, and the limb length here is L by 2, right? Times L by 2 in the anti-clockwise direction. So I can say that I can take the clockwise to be positive and the anti-clockwise to be negative, and I can say this is equal to minus mg L by 2. So and this torque about B needs to be 0 also, right? Because that's what it means to say that it doesn't tilt in any direction. So let me make it equal to 0. So if I make it equal to 0, I get IBB L plus T1L minus mgL by 2 equals to 0. L gets cancelled. I get the value of T1 equals to mg by 2 minus IBB. Okay, that's the value of T1. Now if I plug in that value of T1 here, I can get the value of T2 as well. So T2 will become mg minus this. So mg minus mg by 2, that is mg by 2 plus IBB. So clearly T1 is smaller than T2 and we had to find the value of the least tension. So here tension on one of the ends is lesser than the tension on other ends. Just imagine in this case if we had absolutely no current and no magnetic field. In that case both the tensions would be equal, right? But now because there is a magnetic field, there is a magnetic force which is sort of supporting T1 and opposing T2. So T2 is more than T1, right? So we had to find the least one, so that's T1, and we have gotten that answer to be mg by 2 minus IBB. So you can write it as mg minus 2 IBB upon 2. So you'd find that option number C is the right option.
For more videos and live lectures on the JEE, click on the subscribe button now.